Hello, Year 11. I bet you all missed my voice massively. Lucky ducks, we're back. Going to do a little bit of a starter to A-level chemistry for you. These are completely without obligation. You don't have to do them. They're just something to pass the time if you are as bored by this lockdown as I am. Got my old chemistry books out and have sort of gone over, or will go over, a couple of topics for you. If you are completely disinterested in this, and nobody watches them or no one engages with them, that's absolutely fine. Apart from my hurt feelings, I'll just stop making them. It's no massive problem. Let me know if you want me to continue or would rather plead with me to stop. We are just going to look at today sort of one of the first topics of A-level chemistry. It's very much a continuation from GCSE, so it should be fairly familiar to all of you. It just goes on a little bit more, gives you a little bit more depth to some stuff that we looked at GCSE, so it shouldn't take too long, and I'll try and find some questions online so that you guys can have a practice afterwards. Okay, so we're just going to look at the structure of the atom. We're going to remind ourselves what an isotope is, remind ourselves of this relative atomic mass, and what we'll look at that's new is how we came to find these relative atomic masses. Good. So hopefully, despite a few weeks off school, you can still all remember roughly the structure of the atom. You can remember where we find the mass, where we find what all the different charges are, what my different subatomic particles are. If not, that is something that you're definitely going to want to be going into A-level chemistry being nice and aware of. So these are my subatomic particles: electron, proton, neutron. My mass for an electron is 0, proton is 1, neutron is 1, and these are my charges, and these are where they're found. This is information that you will need to keep with you throughout your chemistry career. You probably need to know it for a bit of physics, a bit of biology as well. Those of you that are doing multiple A-levels, this is just good information that you're not going to be able to escape. And actually at A-levels, these numbers change ever so slightly, or at least you need to be aware that of these specific numbers. So an electron, we can't get away with saying a 0 anymore. We have to say it's 0.000544. And a neutron is 1.001375. It is just something to be a little bit more aware of. It is unlikely that you're ever going to have to do masses with that information, unless it's changed a lot from my days doing A-level chemistry, which is entirely possible, as depressingly it was about 10 years ago. Okay, and then we can go on to remind ourselves of what isotopes are. Same number of protons, different number of neutrons, and all elements to some degree or another have different numbers of isotopes. They have some isotopes that might be much bigger, much smaller than regular. There might be lots and lots of those isotopes, or they might be rarer, but they have all elements will at least have some degree of isotopes out there. And we can remember that it's the neutrons that change, not the protons or electrons, because if protons changed, if electrons changed, the balance would be different, because the number of electrons and protons is always the same, so that my atom's always neutral, and so the overall charge is 0. If the number of protons or electrons changed, it would no longer be an atom, it would be a charged atom, which we call an ion, and so it couldn't exist in the periodic table. It wouldn't really exist in real life. It would be very reactive. It would want to get rid of that charge, and it would disappear quickly. Okay, so isotopes then, they link to what we think of as relative atomic mass, which is the bigger number on the periodic table. Okay, it's this number along the bottom, And we call it relative atomic mass because each one of these numbers is relative to 1/12 of carbon-12, which is a particular element of carbon. And we weigh all our elements relative to 1/12 of carbon-12 because that's a nice number because it was 1 and it means that all our elements are weighed relative to that. It is easier than using grams or kilograms, which would mean that all our atoms would weigh a very, very small amount, and it would be a bit of a pain to write that out every time. So instead, we calculate them all relative to this one element, and specifically 1/12 of it. But what we are looking at today, what is new information and what sort of A-level information, is why these numbers here at the bottom, they're not whole numbers. So often at GCSE, we would cheat a little bit and I would round these numbers up for you. So lithium would be 7, carbon would just be 12, chlorine we might say is just 35. Or at A level, you'd now have to say lithium is 6.9, chlorine is 35.5. You do it to 1 decimal place. And the reason for this is that this mass number at the bottom is not a whole number because it is an average of all those different isotopes, okay? It's a weighted average, in fact, which means that it takes into account not just the mass of the different isotopes, not just the number of neutrons of the different isotopes, but also the abundance of each one of those isotopes. So if there's lots and lots and lots of one of those, it will be, that mass number will be closer to the mass of that particular isotope. Whereas if there's very few of that isotope, then it will barely register at all. And if that's a little confusing to you, just hang on, we'll look at the numbers behind it in a minute and it makes it a lot easier. Okay, if you look back and think here, the reason that this is just over 12 is because there are some isotopes of carbon out there that don't have 12 neutrons. They have that don't have a mass number of 12, they have a mass number of 13, and so it nudges slightly towards 13. It's very rare though, and so it's barely over 12. There are the vast majority of isotopes of lithium have a mass number of 7, but very few of them have 6, and so it just drags it ever so slightly in that direction, and so on. We'll look at the numbers, it'll make more sense. Okay, and mass spectrometry is how we find the abundance and mass of different isotopes. It is a piece of equipment that you use to find the mass abundance of different isotopes. That's all it really is. It can do. It's actually a very useful thing to do. Use mass spectrometry loads in chemistry, particularly if you go and do degrees and things like that. So it's quite clever. But all you really need to know about is that it exists and vaguely how it exists in this diagram here. Okay, so you grab a load of elements, a load of atoms of chlorine or carbon or whatever else it is, and they are all neutral. And you've got 0 charge on it, and what you do is you ionize them. So you knock some of those electrons off and now they're positively charged. And you want them positively charged so that you can accelerate them, so you speed them up massively, and then you run them through this magnet here. And that magnet, because my atoms are no longer atoms, they're ions, they get deflected. And depending on their mass, they get deflected a different amount. So if you think of your atoms as people, and you get 10 different people of all different masses, and you speed them up and then throw them around a sharp bend like this, and instead of an electromagnet there, you've got a water hose and you're spraying them all with water, their mass will affect how much or how they are deflected by that water, how far they are pushed, or how difficult they find it to cross that bend. And as they come around the corner, they'll be deflected different a different amount. And the same thing happens with your atoms. They come around here, they're deflected a different amount, and then you detect them down there, and you can detect how much they've been deflected. If lots of them have been deflected one way, then lots of them must have a particular mass. If lots of them, or if very few of them have been deflected the other way, then few must have that other mass. Okay, and the detection creates a graph which lets you see what the mass of the different atoms are and how many of them there are, their relative abundance, which we use as a percentage. Okay, so if all that's a little bit confusing, that's absolutely fine. It's these graphs that are the most important thing. So by putting your atoms into your mass spectrometer, they fly around, they all deflect different amounts, and at the end of it you get this graph. And this graph tells you that you've got a few elements with a mass number of 10 and more elements with a mass number of 11. Okay, and if you went and looked on the periodic table, you'd find that boron was that element that's got a mass number somewhere between 10 and 11, and this has got 20% of boron 10 and 80% of boron 11. You just need to read it across. Generally in questions though, you get given these percentages, you don't need to worry about reading them, and you can use these numbers to calculate the relative atomic mass, to calculate the number as it would appear on the periodic table. And this is just about following a process. So you've used your graph to find that you've got 20% boron 10 and 80% boron 11, and now you're going to work out this relative atomic mass, this mean, and you just have to weight your mean slightly more towards the thing that's bigger. And we do this in 2 steps. So our first step is to calculate the mass times the abundance of each isotope. So that means timesing your percentage, 20 times by 10, 80 times by 11. Okay, and you get these 2 numbers here. And it doesn't matter what the percentage is, it doesn't matter what the mass number is, you just times these 2 numbers together. And then secondly, you add these values up and you divide it by 100. Okay, you divide by 100 because we're dealing with percentages, and that's how we get it back out of a percentage. So we can add those 2 numbers and divide by 100, and it comes out at 10.8. And if we then go and find boron on our periodic table, you'd find that it's got a relative formula mass of 10.8. Okay, so I'll go through a quick other example of that on pen and paper. I will try and find some questions, post those underneath so that you can have a go at those if you want to. Okay. Good. So what these questions would look like in the real world is something like this: a graph of your mass numbers along the bottom and percentage abundance up the side, as we just looked at, and then it might say calculate the relative formula mass, that should be. So you can see it just makes it genuine, just like back in class. Nice little mistake, deliberate obviously, just to keep us all on our toes. Calculate the relative formula mass of the above element and use this to identify it. Okay, so you're given the graph and it's just about following those steps that we just looked at to identify the element. So it is just the same steps again. So 1, we do our percentage times by our mass. So 35 times by 75.78 is one calculation. Then our second calculation would be 37 times by 24.22. Okay, and we just stick that in our calculator. All going to need to go out and get yourself one of these proper calculators for your A-levels at some point. Very exciting purchase. I think this is still mine from my A-levels. So I've looked after faithfully all this time. Okay, you've got those two numbers there. They look a bit big and a bit scary. General advice in A-levels, probably the same in GCSE, is try not to round your answers until you do the final calculation, so keep them all as ugly numbers with lots of decimals until the very end. And our second step is to add these two numbers together and divide by 100. Okay, so add 2652.3, then divide that by 100, and your answer comes out at 35.5. Okay, so that's the relative formula mass of my element, and then it's just a case of finding that on the periodic table. So you go to your periodic table, whether that is your lunchbox periodic table that I'm sure you've all got, or your mug periodic table that again I'm sure you've all got, or if you're really struggling to find it, you might go to your second periodic table mug, which are all things I genuinely have, which people have bought for me. It's almost like my family think I'm a horrendous nerd. If you did eventually find it on your periodic table, you'd find that that was chlorine over in group 7, because it's got 7 electrons in its periodic table. Chlorine is the example they like to use a lot for this, because it comes out flat in the middle of two numbers, even though those aren't consecutive numbers there. Okay, so that shouldn't have been too long. Hopefully it's not too horrendous, a little way of dipping your toe back in some new work for you all. I hope you're all safe and well and enjoying the fact that you're not doing exams rather than stressing about the fact that you're not doing them. Hopefully not long till you're all back. We're all looking forward to seeing you all again. Bye bye.